Hello, everyone. My name is Slater Heil, and I am a distance student in CSE 7316 Software Requirements. And I'm going to present an overview today of an article regarding enhancing automated requirements traceability by resolving polysemy. First, we're going to review why this research is important. Requirements traceability provides critical support throughout all phases of software engineering. Automated tracing based on information retrieval reduces the effort required to perform a manual trace. Unfortunately, IR-based trace recovery suffers from low precision due to polysemy, which refers to the coexistence of multiple meanings for a term appearing in different requirements. Requirements traceability is defined as the ability to describe and follow the life of a requirement in both a forwards and backwards direction. It has been shown that requirements traceability is vital for other activities throughout all phases of software engineering, such as program comprehension, change impact analysis, requirements reuse, software maintenance, refactoring, test generation, and verification and validation. In practice, requirements traceability can be achieved by managing trace links between software artifacts, like from high level to low level requirements, and traceability information is not created as the process unfolds. What is the motivation for this research? This research revolves around the manual generation of trace links, which can be very time consuming and still prone to error. Information retrieval methods have been introduced for automated trace links generation. IR-based approaches take a requirement as the trace query and return artifacts with high textual similarities as candidate links. Since software engineering is an iterative process with each iteration building on the previous, it can be easy for developers and stakeholders to lose sight of the original intention for which the software was developed. As we have discussed previously in class, these iterations can be compared to an onion, and requirements traceability is a quick method to peel back these layers. In natural language processing, the phenomenon that two terms refer to the same real-world entity is called coference. Next, we'll discuss the novelty of this research. This research presents a novel method based on artificial neural networks to enhance the capability of automatically resolving polysemous terms. The core idea is to build an artificial neural network model which leverages a term's highest scoring coreferences in different requirements to learn whether this term has the same meaning in those requirements. Methodology. After manual analysis of 6 open source projects, it's been determined that 52.67% of the incorrect links that are retrieved contain polysemy. This research was based on the evaluation of 6 open source projects which had been completed in 2 benchmark data sets. The projects were then evaluated manually and independently by 2 domain experts to identify incorrect links. The study compares a new method to those currently being used, such as the vector space model and latent semantic indexing. It is possible that 2 artifacts would likely be mistakenly linked together by IR-based automated tracing approaches, such as the vector space model, which represents all artifacts as a bag of words and therefore fails to recognize the artifact's polysemy information. Currently, only latent semantic indexing is considered to be able to resolve the polysemy problem. By using LSI space, it hopes to preserve important latent semantic structures of documents as well as to remove noise. A polysemous term with multiple meanings is represented as a single point in space. The methodology presented in this article looks to improve upon these previously implemented methods. A better solution for the polysemy problem is to have an automated way to detect the fact that a particular term has several distinct meanings and to place this term in several points in vector space. Artificial neural network techniques have been successfully applied to solve many natural language processing problems. In this paper, it is proposed that an artificial neural network-based approach to enhance the capability of IR-based requirements tracing by identifying polysemious terms and requirements. The core idea is to train this ANN model, which leverages a term's high-scoring coreferences in different requirements to learn whether this term has the same meaning in those requirements. Comparing the newly proposed approach with LSI to evaluate their abilities to resolve polysemy, the results showed that this approach outperforms LSI, thereby enhancing the accuracy of requirements trace link recovery. Next, we're going to review some of the techniques mentioned in this article. First is the vector space model. VSM is fundamental to a host of IR operations ranging from scoring documents on a query, document classification, and document clustering. This approach utilizes a methodology called cosine similarity. The basic tenet is that the same term is used to express the same meaning, and documents share more terms are more similar than documents with only a few terms in common. Since some terms have multiple meanings, polysemious terms in a user's query will literally match terms in documents that are not relevant to the user's information need, thus causing rapid degradation of precision. Next is the latent semantic indexing. LSI assumes that there's some underlying or latent structure in term usage that is partially obscured by variability in term choice. SVD, a statistical technique, analysis allows reduced space to keep major associative patterns of term usage and ignore less frequent term usage, which can be described as less important meanings of certain terms. However, it works while only one usage pattern or meaning of a polysemious term frequently appears in the given document collection. If the frequencies of two or more meanings of a particular polysemious term have no significant difference, it will create a serious distortion and cause more imprecision on retrieval results. Another approach mentioned in this article that can be used to detect polysemy is part of speech tagging. Recent research reveals nouns and verbs carry higher information values than other parts of speech, capturing main actions and objects in software artifacts. Next, we will review the study implementation used in this article. All 6 projects use the issue tracking system JIRA to manage the requirements and other textual artifacts. Stakeholders have defined relationships between artifacts in the JIRA system. The 6 projects are in different domains. The chosen projects are implemented in different programming languages. A particular term may have specific meanings in programming languages. This allowed for the researchers to test the performance of their approach on distinguishing terms, programming language specific meanings with their general meanings. In addition, with the change of time, the meanings of terms may also evolve. So all 6 open source projects are long-lived projects. The more terms of a requirement, the more polysemious terms it tends to contain. So the length of the 6 projects chosen vary so that the methodology can be tested over a representative sample size. IR-based trace link recovery approaches rank all links by their similarities with a requirement. Only the top-end trace links are returned to developers. To study the impact of polysemy on IR-based tracing, the vector space model is applied on all requirements which have been linked to other artifacts. All requirements and retrieve links are then analyzed by 2 authors of this paper independently to find all polysemious terms, the terms which have different meanings in requirements and false positives. Those 2 authors have at least 3 years working experience on open source projects. They started research on the 6 open source projects and conducted many research and development tasks on those projects. Therefore, they are considered experts with necessarily domain knowledge regarding all 6 of these projects. The polysemious terms identified manually by experts were then used for the training set in the artificial neural networks. Solving polysemy could reduce similarity scores between requirements and incorrect leaks, thus improve precision of the results. The resolution of coherence has been referred to as calculating semantic similarity between terms. The assumption is that if one polysemious term in different artifacts refers to different entities, this term has different meanings in those artifacts. The next is a depiction of process that was used in the researcher's methodology. Next, we'll review the architecture used. The given requirements are first fed into artifact indexing, which includes two steps, tokenization and stop word removal. The output of artifact indexing is a term by requirement matrix. The term pair ranking model is then used to score pairs of terms in the same requirement by passing their distributed representations through a feed-forward neural network, which contains one input layer, one output layer, and 3 hidden layers. The feed-forward neural network is capable of approximating any measurable function to any desired degree of accuracy and can be used to learn any long nonlinear relationships. The output of our term pair ranking model is a term pair that contains T in its highest scoring coherence in the same software artifact. The similarity of two terms is usually calculated by using terms and their preceding and following terms. The size of preceding and following terms directly affects accuracies of approaches. An alternative approach is to treat a term in its highest scoring term level coherence in different artifacts as clusters. And then the semantic similarity of two clusters is used to decide whether this term has different meanings in those artifacts. A term pair ranking model is then used, and those results are passed through a pooling layer and a single neural network layer. IR-based trace link recovery approaches calculate similarities of requirement pairs by using updated term by requirement matrix. Only requirements pairs with similarity scores higher than the certain threshold are considered to be related to each other. Next, we'll review the term pair ranking model. A multi-layer perceptron is more suitable to learning nonlinear separable patterns in most data in the real world is nonlinear. The term pair ranking model produces a score SM of A of M, representing their compatibility for coherence with a multi-layer perceptron. The vector is computed from not only the term itself, but also the distribution of terms. Therefore, for a particular term, its embedding representations under different contexts are different. Vector model of meaning is considered as the most common way to compute semantic difference. Using this process, scores are fed into a feed-forward neural network model to learn whether a term in different artifacts has different semantic meanings. The detailed information of input features is shown as follows: the two preceding words and the two following words, the POS tag, or part of speech tag of the mention, the distance between the mention and its candidate antecedent in sentences, and string matching features. This produces a score to a mention and its candidate antecedent representing their compatibility for coherence. The model is then trained using a backpropagation algorithm. In conclusion, the purpose of the term pair ranking model is that for a particular term in a requirement, finding the most related terms inside the same requirement. In term pair ranking model, all terms are from the same stakeholder, and therefore no stakeholder features are considered. Using the cluster pair ranking model, this may come from different requirements created by different stakeholders. Therefore, stakeholder features shall be considered while computing cluster pair compatibility for coherence. The authors then use the output of their cluster pair ranking model to update term by requirement matrix. The updated term by requirement matrix is incorporated into IR-based approaches in order to improve the precision of the trace retrieval results. For each project, a 10-fold cross-validation to evaluate the performance of the models is then performed. The primary goal of the models is to automatically update term by requirement matrix with the hope that all vector space models, such as VSM and LSI, can benefit from polysemy analysis. In order to evaluate and improve the selection feature, The authors performed the feature ablation study on all 5 feature groups, which includes word embedding, additional, distance, string matching, and stakeholder features. The feature ablation study is designed to assess the informativeness of feature group by quantifying the change in predictive power when comparing the performance of an approach change with all feature groups versus the performance without a particular feature group. We'll briefly review the summary of evaluation results. The Polysemy enhanced approaches significantly improved the precision, at the same time not increasing the recall on 5 of the 6 projects. This confirmed the author's hypothesis that resolving polysemy will lead to ruling out incorrect links. In addition, solving the polysemy problem leads to reducing similarity scores between requirements and incorrect links. At the same time, solving synonymy problem leads to increasing similarity scores between requirements and correct links. The combination of these 2 effects certainly further improves the approach's accuracy. The authors were able to conclude that methods of solving polysemy and synonymy are complementary with each other, meaning the improvement achieved by resolving both of them is greater than the sum of improvements achieved by resolving them separately. Polysemy is a typical natural language problem which has impacted automated requirements tracing. This paper tries to resolve polysemy by adapting natural language processing approaches into information retrieval-based requirements tracing. Their contributions include quantifying polysemy impact on automated requirements tracing, proposing a semantically enhanced approach to detect polysemious terms, and testing approach with 6 open source software projects and 2 benchmark datasets. Finally, we'll discuss how their methodology can be improved. Separating polysemious terms combined with a good way to adjust their weights may further reduce the similarity score, thereby helping ruling out false positives. Further analysis of the reasons calling polysemy is necessary and will help with feature selection. Incorporating a more substantial data set would allow for a better test of this methodology and provide more confidence in its accuracy. Improving the artificial neural network used in determining the context of terms in specific artifacts would allow for better analysis of terms used by the stakeholders in those artifacts. The authors also mention that their future work will include finding and testing more features, building enhanced automated requirements tracing with other neural network models, and training a new model to resolve both polysemy and synonymy together. Thank you for your time. And if you have any questions, please feel free to email me. My email address is sheil@smu.edu. Thank you.